Welcome to everyone for this advanced reinforced concrete design course. We will be starting this module 1.2. We are in the module 1. Today, we are going to discuss about what are the various design concepts that are there and how the design philosophies have evolved over the period of time. So, after attending this module, the student is expected to learn about what are the major objectives of structural design and should be able to explain the need for design codes. And we have different types of concrete designs that are available. So, we'll talk about it depending upon what kind of design that you're doing. So, we will talk about that and we also going to see the differences between when you analyze a section versus when you design the section. So what are the differences that we'll briefly will talk about that. And the philosophies, as I've told you, it has evolved over a period of time. So we will talk about how the philosophies have evolved. So briefly we'll talk about that. Finally, we will conclude the session for this module with the difference in design philosophies between American Concrete Institute approach and the Bureau of India standard approach. Right. So first, let's briefly talk about what are the objectives of structural design. I think so the first and foremost criteria is the structure should be safe. That means it should have adequate strength for various types of load action that the particular structure is going to see through. So the strength and safety is the fundamental requirement that we need to be careful about. So strength is basically to resist safely the stresses induced by various loads that particular system, the various structural members are going to see, right? The next is stability. Of course, the structure that what we are designing, it has to be stable. It cannot overturn, it cannot slide, or some of the members or as a structure as a whole cannot undergo buckling. Okay, so under the action of load. So the stability is also very important requirement in structural design, right? And the structure should be serviceable. Okay, so what is the meaning of serviceability? So it should ensure a satisfactory performance under service load condition. So the strength may be adequate, but if the structure is not serviceable again, it is not going to serve the purpose. So it should actually contain adequate stiffness to make sure that the deflections are not very high, and the structure should not have larger crack widths, or most of the time we want crack free structure in a reinforced concrete element, and vibrations also should be within acceptable limits. Yeah, so this is just a picture which shows a reinforced concrete beam that was tested, and you can see this is actually at a very close to ultimate load. You can see that the structural element has undergone severe amount of cracking. This kind of cracking is not acceptable under service load condition. And another important aspect in a structural design is the structure should be durable. So, what is the durability? Basically, the structure should be able to satisfy all the other requirements, okay, and it should be also maintenance free, okay. So, in a reinforced concrete structure, we want the structure to be impermeable, right? So, it should not allow the ingress of deleterious substances. In fact, we have a separate module on durability where we will talk about what are the various degradation mechanisms that the concrete and steel reinforcement undergoes. Okay, so these are, for example, the figure. I think we have also several historical monuments in India, and you can see the Roman concrete, the Pantheon that we talked about in the um, last module. You can clearly see here that it is still standing. So that means if you do good concreting, the structure can stand for a long period of time. So that is the thing, right? Right. So another important aspect is the structure should be the design should be economical, right? So it should also fit within the budgets of the owner who is constructing, and also it should be aesthetically pleasing. Okay, so this is also one of the important structural requirements, right? Okay, so now let's talk about the overview of structural design. And in general, the structure should satisfy these four basic criterions when you design. Okay, so first, it should satisfy the functional and safety considerations, which are very, very important, depending upon what type of structure that you are doing. It could be a building, it could be a bridge, or it could be a nuclear reactor. So the functionality and the safety of the structural element is foremost important consideration. Of course, depending upon the service life of the structure that you're designing, you have to really take care of what kind of materials and system that you're going to use for constructing it. So this is an important consideration. Now we also have constraints. Okay, so we'll talk about again constraints. The constraints for any project would be the amount of funding that is available for the project. Okay, and also sometimes the space availability for a particular structure will be limited based on the site considerations. Sometimes the owner or the client that whom we are dealing with, he or she may not be knowledgeable to the level of appreciating the aspects of the structural design that what we are talking about. Sometimes even the engineering fees, mostly if you're taking care of the, if you're doing a building type of project, the architectural as well as the structural engineering fees also will come into picture. These are the constraints from owner point of view, right? So this is also we have to keep in mind. Now, we need to also be careful about the process that how we are doing. First of all, we should understand, as I said, the needs of the owner. Okay, how long that particular structure, that particular owner want it to be function. Sometimes for a temporary structure, then the design requirements will be different. Then, based on the needs of the owner, first we develop the concept for basically for laying out the structural element. This is called conceptual design. Once the conceptual design is done, then you go to the next level, which is system and member level design. Okay, so that is what we are going to look at in the process. Okay. Right. So the next is also we need to consider the viewpoint of people or the agencies involved. Of course, that includes the owner and client. And then sometimes if it is a very big government project, then we need to take the inputs from government bodies, and we have to take approvals from various government bodies like municipality, state, and central. Sometimes if it depends upon what kind of project that you are doing. And also we need to have a very good coordination between architects, structural engineer, and mechanical and electrical plumbing agencies. So this is also an important. As a structural engineer, we do the design, but it will be executed by somebody else. Usually, it is the contractor. The contractor also should be able to understand the structural drawing and the construction process well. So it is actually a teamwork. If you want to, do a good design and that has to be executed in the site, then all the stakeholders who are involved should be working in tandem, and there should be a good teamwork. Okay, so again, so these are the major consideration that we need to consider. So we need to first consider the functional and safety considerations. We should understand the constraints of the project that is involved in, starting from funding and the space availability and the knowledge level of the owner, and then the process. The process is actually in a stage by stage process. First is the structure should fulfill its functional requirement. Then we, based on that, we do the architectural design, and then we go to the detailed system and member level design. And of course, we have to deal with various type of people who are involved in this process, right? Now, so these are the things. Okay. So the structural adequacy, I think we talked about, it should satisfy the safety requirements, that is from strength requirements, and then serviceability requirement. The structure also should be stable. So these are the things that we talked about: structural adequacy, and then functionality. Okay. So again, the functionality is very, very important. The structure meets all the three requirements, but if it is not functional, then again it is not going to be a good design, right? And it should also be durable. So what is that meaning of durability? Again, we talked about the structure should be able to satisfy all the requirements with very less maintenance. So we'll talk about durability aspects in the coming module. And also the solution that what we are giving, it should be an economical solution. Okay. So ideally a goal should be basically to satisfy all these aspects. Okay. And the structure should have satisfy all the structural adequacy requirement. It should be functional, it should be durable, and also it should fit within the budget that is available. So again, each one of them will take a priority depending upon what type of structure that you're doing. For example, that what you see here is this a nuclear power plant in Tamil Nadu. If you see here, of course, structural adequacy will should be of paramount importance. Economy may not be that critical in the design aspects, of course. And also, the reactor should be functioning, so you design in such a way that it is going to be maintenance free for the service life, right? And this is another example, which is a signature bridge. It was built 15 years ago in Delhi. You can see that again, this type of bridges should be standing for about 100 years with less maintenance. So again, here we need to be, when you're designing for 100 years, of course, your design requirements we need to be careful about. And of course, historical monument, you can see if now I think we are also building various, different statues, right? These are all historical monument. Here, the economy may not be of that critical factor because this is a monument that you're building. Okay, here the functionality, durability, and structural adequacy will take a major emphasis rather than the economy. But if you're doing a simple buildings, this is in fact India's first 3D printed house. Concrete was 3D printed. So depending upon what kind of structural element that we are doing, of course, uh, each of the requirement will vary a little. Okay, so when you do this, so now that we talked about the objectives of the design and how do you requirements, now to help with this whole process, we have different design codes. Okay, for example, what you see here is that IS 456 code, which is for plain and reinforced concrete, okay, which is what predominantly we are going to use in this course. And we also have IS 1893, which is a code for earthquake resistant design of structures. And then we also have a code for precious concrete, which is IS 1343. And this is an American concrete. I've just given again. So different codes are available for designing various, depending upon the type of structural system that you are designing. For example, if you're looking at bridges, we have Indian Road Congress codes are available. If you're doing railway structures, railway bridges, Indian Railway Standard guidelines are available. Now, what is the need for a code, right? A code or standard is set of technical specification that help the design and construction for certain type of structures. So we have varieties of codes and design standards that are available. So what is the need for the code? So basically the goal of the code is basically it's going to ensure if you follow the code provisions in your design, it's going to ensure adequate structural safety by specifying certain minimum requirements for design. For example, you must have seen that span to depth ratio, depending upon whether we are doing a beam or a slab, and depending upon the boundary conditions, it will tell you what are the span to depth ratio minimum that we should follow, right? And also, it will give you minimum deflection requirements that which should be the deflection should be within this specified limit. So, such kind of provisions will be readily available. Okay, so that makes the task of the designer relatively very simple. Often, the results of this sophisticated analysis, like I told you, instead of doing very detailed structural analysis, people have already done. And based on experience, the code gives you in a very simplified formula or a chart. If you follow that, your requirements will be by and large met. So this is one of the advantages. Again, codes also, when different people do design for a same structure, so design is a creative process, right? So depending upon the person who is designing, the sizes of the members and the arrangement, things can be different, right? So, but if you follow certain standard code or codes of practice, it ensures a measure of consistency among different designers. Okay, so that is again one of the purpose of having a code. And most important aspect is codes have some legal validity. Okay. For example, they can protect the structural engineer or designer from any liability, if at all, if there is a failure that is happening due to inadequate supervision or improper material that is used in construction, where the structural engineer is not really liable. In such case, if the structural engineer has followed the design standard design code, then he or she will be protected. It is kind of giving the legal validity, and it is going to protect the structural engineer from any liability issues. So these are some of the things that we need to think. So, right. So we talked about objectives of design, and then we talked about what are the various codes that are available and what are the need for the codes. Now let us talk about what are the types of concrete design that usually we do. Okay, they can broadly be classified into three main categories. The first one is the plain concrete design, and it is usually used for non-structural members. Okay, because plain concrete, we know that concrete is strong in compression, weak in tension. Usually, we don't put concrete under tension. But for some non-structural members, we can use plain concrete design. So when you use such systems, of course, the design will be governed by the tensile strength that we are going to have. Okay, and we have seen in the last class also in the introduction, the tensile strength of concrete is usually varies from 8 to 15% depending upon what type of flexural strength that you're talking about. Either it's a direct tension or a flexural tension. In this case, the beam is subjected to a central point load, which is subjected to bending. So you're going to talk about flexural tensile strength, or is also called as modulus of rupture, right? So here the modulus of rupture, we know that we'll talk about that in the material class. FCR in IS code, it is usually given as 0.7 square root of FCK. Okay, so that is what we will be using it and then calculating that. Next is the reinforced concrete design. That is what we are going to go through in this course for various load actions. So usually what we do to overcome the low tensile strength of concrete, high tensile reinforcement in the form of steel reinforcement is added in the regions to enhance its capacity. Now, though there is a crack like this, the system will not fail. Here, the moment this crack fails, that's it, the failure, right? However, the moment you put reinforcement, now the reinforcement will be able to take the tension. And we know that concrete is strong in compression. So now you can really, the system can take large amount of tensile stresses, and then you can increase the capacity. So this is what the objective of this course is going to be. We are going to focus on reinforced concrete design. Now, next one is the pre-stress concrete design, right? So, pre-stressing again is one very innovative way of tackling the low tensile strength of concrete. So, what does it do? In fact, last class we also talked about history of pre-stress concrete. Eugene Fresnay is considered to be the father of pre-stress concrete. So, what we really do here is we put the concrete in compression even before any external loads are applied, and we apply some pre-compression in the regions where tension is going to develop due to external loads. In this way, we can increase the load capacity at which it is going to crack. Because now that wherever is tension is going to develop, I have put some compression before, that compression has to be nullified and it should reach the modulus of rupture before it cracks. So you generate really a crack-free, nearly a crack-free structural element under service loads. Okay. So usually what we do is pre-stress is applied to concrete member by high-strength steel tendons. Okay. Imagine this high-strength steel as a rubber band. I stretch the rubber band, pour concrete, and then I leave the rubber band. The rubber band or the steel is going to basically squeeze the concrete and is going to put it in compression. So in that way, we can create compression in the regions where tensile stresses are going to develop because of external loads. Okay. So what are the advantages is when compared to classical reinforced concrete design, pre-stressed concrete design produces usually lighter sections. Okay, that means sectional depth requirement for a particular service loads or design loads are going to be very light, and that it is going to allow economic use of longer spans. Okay, so usually if you want to have longer span, we end up going for pre-stressed concrete design. Okay. All right. So these are the three types of design that we usually encounter in concrete systems. One is plain concrete design, typically used for non-structural system, and reinforced concrete design used for regular designs, and then pre-stressed concrete design depending upon your requirements. Okay, and pre-stressed concrete is going to also give you more durability because under service loads we are going to have crack-free conditions mostly depend. Again, in a pre-stress we have type 1, type 2, type 3 design. Let's not get into that, but usually pre-stressing is designed in such a way that under service load these elements are not going to be cracked, so the durability is also going to be higher. Okay, now we'll talk about design versus analysis, right? In fact, design is an iterative process. Okay, so what is that you mean by design? Okay, now I'm just taking one example. You've done the structural analysis. Even for doing structural analysis, first of all you need to assume the dimensions of the member. Okay, so those assumptions of the sizes of the members to start the structure analysis usually governed by some thumb rules. So like what we talked about, span to depth ratio and column dimensions can be come up with the tributary area concept, right? So using that, we first to start the structural analysis, we find our internal force distribution. So what is that internal force distribution? Basically to find out the variation of your shear force, bending moment, axial forces, and torsion on the structural elements that you are designing. Okay, so in design usually is we try to find what type of structural system to be used and what should be the span and what should be the cross section dimensions and the reinforcement. Okay, so this is what design we do. But again, I said span can be fixed based on your functional requirements from architectural consideration. At the same time, the depth of the member can be fixed based on simple L by D span to effective depth ratio provisions that are usually given in the code. Those are derived based on the past experience. Now, and again, cross-section dimensions also can be determined based on the architectural requirements and based on some thumb rules that are available. Once those things are available, what actually we end up doing is making sure that the chosen dimensions are adequate and we find the amount of steel reinforcement that is required to resist the internal forces. Okay. So the designed structure should be able to resist all the forces expected to act during the lifespan of the structure safely without excessive deformation or cracking. So we will talk about it. In reinforced concrete, usually we design for ultimate state, ultimate limit state. Okay, that is for strength, and then we check for serviceability. Okay, but it is not always true. For example, if I am doing a water tank design, then your serviceability condition, that is the crack width condition, will dominate the design. Then we go ahead and check for ultimate strength. But usually, for most of the structural elements, we design for ultimate strength condition and then we check for serviceability, right? So we have to keep that in mind. Now, so in flexure, for example, when I look at this kind of, let's say, beam that we are talking about, Okay, so let's say that I come up with this kind of beam dimensions. Let's say this is B and H. Okay, and I want to design this beam for a demand which is bending moment of mu. Okay, and usually, like I said, to get this bending moment mu, first of all, I need to do structural analysis. Okay, to determine this mu. Now that I fix this dimension B and H, I have to make sure that whether I am able to, I have to basically put some steel, right, to make sure that it is having adequate capacity. Sometimes, if you put steel only on the bottom, one side, you call that as a singly reinforced section. Sometimes, if your MU is much larger and based on the flexural design requirements, which we'll discuss, you may end up providing some steel at the top also. So, this is called as doubly reinforced section. Okay. So, this is what we are going to do. So, this is what the design is. First design is determining what type of structural system to be used, and usually the span will be given by the architectural requirement, that is functional requirement. Once that is fixed, we choose your breadth and depth of the section for flexure, right? And then all we do here is to find out what is the amount of steel that we need to put. AST in this case, let's say this is ASC. Okay, so this is what we are doing. So the known would be basically what is the maximum moment of resistance that is required, and grade of concrete will be given, and what type of steel grade that will be given, that will be known. And B and H, you will assume it. And most of the time, what we do is we end up determining what is the amount of steel that is actually required for your design. Okay, right. Now let's see what is analysis. Okay, is analysis actually design is also an analysis with certain assumptions. We actually do analysis to find the capacity for the assumed level of steel. Okay, but actually in analysis, sometimes what we do is your breadth, depth, concrete strength, grade of steel, the amount of steel will be known to you, and you have to calculate what is the moment of resistance and the curvature at failure is going to be for flexion. This is, I have taken an example only for bending or flexion. So in analysis, what we are really doing is determine the capacity of sections of known dimensions, material properties, and steel reinforcement for any external forces or moments. Okay. So this is again for one analysis for ultimate load condition. Sometimes for service moment, we do analysis to see what level of stresses that are acting on the steel and what is the crack width that is going to be there under the service moment and so on. So these are basically service level analysis. Okay. So, so as I said, design is also actually we do analysis only, but design is an iterative process. Okay. So usually your ultimate moment requirement will be given to you in design. Concrete strength and grade of steel will be given. You will be ending up finding most of the time the amount of steel that is required. Okay. In analysis, the entire details will be given. You are just going to find out what is the moment of resistance and curvature at failure, or sometimes for service moment, what kind of stresses and crack width are going to be there, right? So usually design and analysis are interrelated. So that is what I said. Design also actually we do analysis only. So they're all interrelated, and design is an iterative process. You try different things until you satisfy your requirements. So requirements is basically adequate capacity should be meeting that demand requirement, right?